Okay, so that was the so-called atomic theory of rational functions. We also thought about end behavior. End behavior is what happens as x approaches infinity or negative infinity. And we had several ways of thinking about this. One way of thinking about this was in terms of dominating terms. So you think about the highest degree term in the numerator and the denominator, realize that as x approaches infinity, the actual number that the numerator will be is very close to the contribution from the dominating term, because everything else is going to be very small compared to what that is when you plug in large x values. So what that means is that your original function is approximately equal to what you'd get if you ignore everything else, but only when x is approaching infinity. And not exactly equal, approximately equal. So that was the sort of dominating term way of thinking about it. In this case, this ends up simplifying as negative, so the 7 and negative 7 divide to be negative 1. X squared divides 2 of the x's up here. So this is approximately x. And then you ask, okay, well, originally we wanted to know, what do the y values do when x approaches infinity? What I know is they do approximately the same thing as this function.
Negative.
Oh, thank you. So they do approximately the same thing as negative x. So what does negative x do as the x values approach infinity? The y values are approaching negative infinity. So that's told us there can't be a horizontal asymptote here. So what kind of asymptote is there? Probably a slant asymptote. Because remember, we learned polynomial division. And if you imagine performing the division, if you have a cubic thing divided by a quadratic thing, you'll probably have a linear thing left over. So that tells you that you probably have a linear function as your slant asymptote, and you could actually perform the division to figure out what it is. If you perform the division, you would get something of this form. You would get whatever the solution was after you divide, plus some remainder. And the remainder is always divided by whatever expression you were originally dividing by. So this form makes it a lot clearer what the asymptote is. This expression tells you an equation of an asymptote. And what makes it an asymptote is that our actual y values are getting closer and closer to these y values. How do I know they're getting closer and closer? It's because as x approaches infinity, this whole term is approaching 0. So that means the further out I go, the more I can ignore these, or rather, the closer my y values are getting to be to these y values. So that's what makes that an asymptote. I think that, oh, and then the last thing that we talked about very briefly was the slightly more formal version of the dominating term approach, which was note whatever the highest degree term is and multiply by the fancy form of 1. So this is thing divided by itself, so it's not changing the values. It does introduce a discontinuity, but since we're only looking at what happens as x approaches infinity, we don't care about that discontinuity. And then you can multiply this in, you can distribute this in to each of the terms, and then it will simplify in a way that will make it a little clearer why the dominating term is the thing you pay attention to. And you're not required to do that analysis, but I just wanted to offer it as a slightly more formal version of the other approach. Thank you. Questions about